Now let's look at matrix transpose. So we have this matrix here A, which is a 2 by 3. That is, it's got 2 rows and 3 columns. We want to form the transpose of this. So we write the A with a little t. So this is read A transpose. Now in order to transpose, what we do is we take the rows and we make them into columns. So this row here, 1, 2, 3, becomes the column 1, 2, 3. And the next row, 4, 5, 6, becomes the column 4, 5, 6. Equally, you could look at it in terms of the columns becoming rows. We could say column 1, 4 becomes this row here, 1, 4. Column 2, 5 becomes this row 2, 5. And column 3, 6 becomes this row here, 3, 6. So either way you want to look at it, this is the transpose. So we know that the rows become the columns. So it means that whenever we get the result of the matrix transpose, it's going to be in effect a different shape. So for example, in this instance here, it's a 2 by 3 matrix. That's 2 rows and 3 columns. But when it's transposed, the number of rows becomes the columns, and the columns becomes the rows. So it means that a 2 by 3 will become a 3 by 2. Now what's interesting here is that all of the matrix transformations we've looked at so far maintained the shape of the original matrix. So for example, when we did addition and subtraction, we started off with a 2 by 3 matrix and we finished with a 2 by 3 matrix. But now when we're doing transpose and whenever we move on to multiplication of 2 matrices, we're going to have the output matrix, which will be potentially different from the input. So in this instance here, we can see that the output's different because the rows and columns are swapped around. Now let's say, for example, we took this example here where it's just a 1 by 3 matrix. So whenever we transposed this, it would give us a 3 by 1 matrix. But whenever we represent this here actually within our computer, all we're going to have is the number 1 in one memory location, the number 2 in the next, and the number 3 in the memory location after it. So it means that whenever we represent this matrix here, we're going to have exactly the same. We're going to have number 1, then number 2, and then number 3. So in this instance, what is it that separates this matrix from this matrix? Because clearly they are 2 different matrices. So what distinguishes these are the row and columns. So it means that we have to be very careful that whenever we do a matrix manipulation, if the row and column values change, we have to make a note of that. So we have to take a copy of the new row and column values. So that's what we're going to do in the piece of code, which I will show you next. Now we have our 2 pieces of code. The one on the right is the calling function, the one on the left is the subroutine. So we have in the calling function a 2 by 3 matrix. So the matrix we're going to use is 1, 2, 3, and then the next row is 4, 5, 6. So the length of this is 6. The m and n values are 2 and 3 because it's a 2 by 3 matrix. Now the answer to the transpose again is still going to be of length 6. And the extra thing we've got added in here is the fact that now the new matrix that we get out, it's got different m and n values. They're actually switched. So we really need to take a note of this. So the new matrix that comes out will have new m and n values, and I've called those mt for transpose and nt. Okay, so that's the extra section we've added in here. So we're going to push the matrix, we're going to push the length, we're going to push the value for m and the n, we're going to push the address of mt, the address of nt, and the address of the trans, okay, so that's where we're going to store the results. We're going to jump to the subroutine. It will run through the subroutine and it should return the correct values into trans, so there'll be 6 values, and it will also return the 2 values for the new M and N values for the final transposed matrix. And then it will finish, and that'll be the end of the program. So that is the calling function. So let's have a look at the subroutine. Now the subroutine, it's a bit more involved than previous code, so we'll take our time and we will work through it. But remember, you will have access to these within the actual resources section. You can download and you can play with them as much as you want to see how they work. Now this is quite a long piece of code, so I'm not going to talk through every line of it in detail. It would just take too long and it would be quite boring. So what I'm going to do is just go through roughly how the code works. Remember that you can download it within the final course, and you can actually run it up in the CPU, and you can look at it running one single clock pulse at a time. So we're going to start off with basic housekeeping. We save the original registers to the memory locations for safekeeping. We pop off our values here, and remember they're in reverse order. Now a thing to remember here is that if we have a bracket round here, it means we're pushing the actual value. If we don't have a bracket, then we're pushing the address of that value. Okay, so we pop these off, and the first thing we're going to do is we're going to swap the value for our rows and columns. So we've got the rows and columns in this particular example is 2 by 3, and those are stored in a memory location M and N. And as I mentioned earlier, we're going to have 2 new memory locations for the new transposed values for our rows and columns, and those are going to be held in MT and NT. So this little bit of code here just swaps those round about and stores the values in those new memory locations. And then we clear off the registers that we used here so that they're clean and ready for the next part of the code. Now the next part of the code here, what we're going to do is we're going to assume we're working with either a row value of 1 or a column value of 1. If we have a row value of 1 or a column value of 1, then all we're going to be doing is just copying the values out into new memory locations. So remember, if we had, for example, a 1 by 3 matrix and it was just 1, 2, 3, then when we transposed it, it would become, again, it would be 1, 2, 3. But as far as our memory is concerned, all we see is 3 numbers sitting in consecutive memory locations, number 1, number 2, and number 3. Okay, and that's the same for a 1 by 3 matrix or a 3 by 1 matrix. Now the only thing that differentiates both of these is the actual row and column numbers, and again that's why we've done this here, generated the MT and NT. Okay, so we make the comparison and then we jump down to single if either the row or the column has a value of 1. So we come down here, and I'm not going to talk through every piece of the code here, but what it does is it just copies those values into the trans, okay, so to the transposed matrix. Okay, so just copy them straight over, and then it would just finish that up, and we would load the values from the memory back into the registers. Okay, now that's if we were dealing with a matrix that either had a row or a column with a value of 1. So let's look and see by an example how the actual algorithm is going to work in order to transpose. So let's say we start off with, say, the matrix 1, 2, 3, 4, 5 and 6. Now the way this matrix is stored in memory is just in consecutive locations, so it's 1, 2, 3, 4, 5 and 6. So we just store them in consecutive memory locations. Now whenever we transpose this thing here, it's going to give us, the rows become the columns, so it means we're going to have the value of 1, 3, 5 and then 2, 4, 6. So this is the transpose of this. Now it means that the transpose one is going to be in memory in the following order. It's going to be 1, 3, 5, 2, 4 and 6. So it means in order for us to generate these numbers, we're going to start off with this number here in the same memory location. But in order to generate this, we're going to have to go from 1 down to 3 and then 3 down to 5. Now once we've done that, that's us done 1, 3 and 5, we'll have to come back to the beginning here, and then we're going to have to add 1 on to that number, the memory location, and then we're going to have to go from here down to 4 and here down to 6. So that's the basic principle of how we're going to do the transpose. And you can see here that from this point to this point, we're going to be adding on the value of n. So what I mean is, if this matrix here is going to be a 3 by 2, so this is the m and that's the n. So we're going to be adding on the value of n. So we start here and we add on the 2 and we add on the 2. And then we only do that a certain number of times. So the actual number of times we do it is, whenever you have a wee look and work through it yourself if you like to, we've got to do this m minus 1 times. So in this case here, the m minus 1, so the m here is 3, so we've got to do that 2 times, okay? And you can see here we've done it 2 times. We've done it once, twice, okay? So we're always doing it m minus 1 times, and we're going to jump n numbers each time. And then whenever we've finished that, we come back to the beginning here, we add the number 1 on, and we do the same for the next lot. We're going to jump n, okay, and we're going to jump that n distance m minus 1 times, okay. So maybe you can sit down with a pen and paper and have a wee look and test this out for yourself, but it does actually work like that, and I have coded that algorithm into our assembly language. So let's quickly see that in the assembly language, then we'll load it up in the machine and we'll see it working. So the final part of the code is this little part here, and the outer loop and the inner loop. So we start off with this little part of the code here. Now the value for the very first entry still remains the same. So if I have a 1, 2, 3 and I transpose it, the 1 goes to the same position, okay, so there's never any change. So we deal with that here, and it just shifts the 1 value, or the very first value, to the transposed position. Now it then heads on to the inner loop, so it jumps here to the inner loop, and the inner loop is going to take the value and it will be adding 2 onto it. So for example, it will be jumping from 1 to 3 to 5. Okay, so this loop here does that jump, and it does it m minus 1 times. So once it's done that m minus 1 times, it then jumps out of the inner loop and goes to the outer loop. So the outer loop then adds the value on, so we get the new position. So instead of going the 1, 3 and 5, it jumps down to the position where it says 2, and then it jumps back into the inner loop, and then it does the 2, 4 and 6. So that's how it works. The inner loop does the ends m minus 1 times, and then the outer loop shifts the value down by a value of 1. There's a bit more involved in shifting the value down because I have to reset some of the values in order to get it to work within the inner loop. But that's the basic principles of it. Again, if you get stuck at this and you want to look at it in more detail, you can load it into the machine and you can chase up every single 1 and 0 for every single clock pulse, and you can check and see every single line going live within the CPU. And that's the whole point of the course. You can break it down into absolute infinite minute detail, or you can have a look at it just as a kind of top level view. It's up to yourself. So let's load this into the machine and we'll see it working. I have loaded the subroutine into the ROM and the code into the RAM. Now the example we're going to work through here is the 2x3. So we're going to put in 1, 2, 3, 4, 5, 6. When we transpose it, the values are going to run 1, 4, 2, 5, 3, 6. And it won't be a 2x3 matrix, it'll be a 3x2 matrix. So let's run this up just now. Now it takes a little bit longer to run because it's having to load a lot more values into the memory. But once it gets loaded up, it tends to run through quite quickly. And I have ran through matrices which are 30 by 30, and it runs through within about a minute. So you can see the values coming through here now. And it's working through the first row, and it'll jump down to the next row. And that's it cleared it off, and that's it finished. So we'll stop this and we'll drop in, we'll see the actual values. So it's maybe a little bit small, so hopefully you can see it here, but we've got our matrix which has got values 1, 2, 3, 4, 5 and 6. The length of the matrix is 6, and the row and column count, the M and N values, are 2 and 3. Now for the transposed matrix, the transposed matrix are going to have the values. Now I'll bring them up here as well so we can see them here. So the transposed matrix is going to have the values 1 and 4, 2, 5, 3, 6. So we come in here and you can see the 1, I'll click on that, so 1 and 4, 2 and 5, 3 and 6. Now the important thing here as well is now the M and N values are swapped round about. So the M is now a 3 and the N is a 2. So that's important that we continue and maintain that information on the row and column count for the matrix. So let's quickly go ahead and I'll load up another one, a much larger one, and we can see it working. Okay. Let's look at the final transpose here in the video. So we're only another couple of minutes to go. We're going to do the transpose of a 3x8 matrix. So the matrix is going to run 1, 2, 3, 4, 5, 6, 7, 8, and in the next row 1, 2, 3, 4, 5, 6, 7, 8, and in the next row 1, 2, 3, 4, 5, 6, 7 and 8. Now the actual code is here. So this is the calling function. So there's the matrix. It's 32 values in length. It's a 3x8. And the transpose will also be 32 values. Now what I've done is I've put it into ChatGPT and asked it to transpose it. So I've put the matrix in here and asked it to transpose it for us. So this is the transpose matrix. So it's going to run, if it runs right, it will run 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, and so on and so forth. So let's run this up and see whether this actually does it. Now it takes a little bit longer because we're going to have 3 times as many values going in, but we don't need to watch all of it. What we can do is we'll go in and have a look in the actual memory here, and we should be able to see the values getting loaded in. So this is the RAM here where the results are going to be held, and you can see that we're going to be putting in the original values for the matrix, which are 1, 2, 3, 4, 5, 6, 7 and 8. And again 7 and 8, and again here. And there you can see the final results are starting to come out. You can see the value 1, 1, 1, 2, 2, 2, and the next lot will be 3, 3, and 3, 4, 4. So hopefully you can see those, and this will run 555, 666. So I think we'll just let it run because it's running quite quickly and it's not that far to go, okay? And then we'll have 7, 7, 7, and 8, 8, 8. And that's the end of the code. So that's a transpose this 3x8 matrix. So again, you'll see it coming to an end here just in a second. So I've actually ran through much larger matrices, actually like 30 by 30 matrices, okay? And it runs through no problems. So let's close that off. So that's, you can see it's finished. And you can see that the final values should be the 8 by 3. You can see them here. So it's gone from a 3 by 8 matrix to an 8 by 3 matrix. So that's us done the transpose. It was quite a long and involved video. In the next video, we'll go on and look at multiplying two matrices together. And that should be us finished the matrix stuff for our mathematics library. And then we will be able to move on to the complex numbers. So thank you for listening. I'll get you on the next video. Goodbye.